Assalamualaikum and good evening to our lecturer who is Dr. Roshaini. I'm Nurhasha Alia with my team members who is Hani Nur Akila and Nurul Nafiza. We'll do our video presentation as our assignment. We decided to choose our title of chapter 4 in textbook, which is Rotating Coordinate System in Non-Inertial Reference System, and we choose to explain how the wind turbine make a rotation in coordinate system. In my part, I will explain on what the concept in rotation and application of law. In a rotating coordinate system, a free particle moves in a way that appears to be affected by three forces. The first one is the centrifugal force, the Coriolis force, and the Euler force. These forces arise only from the rotation of the coordinate system. Let us take a look in this figure below on how motion of a particle is affected by the rotation of a coordinate system. Suppose a vector is resting in the frame which is rotating with respect to some fixed frame, as the vector A is equal to vector A in x-axis plus vector A in y-axis plus vector A in z-axis. Then the derivative in the rotating system as the equation below. So the derivative in the fixed system we got as the equation below. Now consider for velocity vector is equal to derivative of r is equal to vector omega times by vector r, and then we will get like equation below. Then we have an operator. Derivative is equivalent to omega vector times by, and then therefore we will get the like equation below. So the new equation can be written as equation 3, where fixed derivative vector A is equal to rotation derivative vector A plus vector omega times by vector A, and therefore they will be the equation below. Or another derivative or expression in 3 we got as this. If we substitute the position vector r in place of A, the acceleration and velocity can be obtained from 3 and 4 as to equation below. As a result, for the Coriolis acceleration equation we got is 2 vector omega times by rotation vector v, and for the centripetal acceleration equation we got is vector omega times by vector omega times by vector r. For the angular acceleration of the body due to acceleration of rotating axis equation we got is vector omega times by vector r. And then just for our knowledge, the definition of Coriolis acceleration is the acceleration due to the rotation of the earth experienced by particles, water parcels for example, moving along the earth's surface. For the second one is centripetal acceleration, is defined as the property of the motion of an object traversing a circular path. And for the last one is transverse acceleration of a particle result from any angular acceleration of rotating system. Applying the laws of motion in non-inertial reference system involve accounting for fictitious forces that arise due to the acceleration or rotation of the reference frame. These applications are crucial in various fields, ranging from engineering and physics to meteorology and astronomy. Below, we explore how these principles are applied in different contexts. The application of Newton's law of motion in a rotating coordinate system requires some modification to account for the non-inertial nature of the rotating frame. The key points are, for the firstly, in a rotating frame, an additional term appears in the time derivative of a vector known as a Coriolis term. The rate of change of a vector A in the rotating frame is derivative vector A is equal to rotation derivative vector A plus vector omega times by vector A. For the secondly is applying this to the velocity vector u, the equation of motion in the rotating frames become as below, where r is the positive vector. The additional terms are the Coriolis force is 2 omega times by u, and the centrifugal force is omega times by r. Next, if the particle's acceleration is increased by the Coriolis acceleration, then Newton's rules can be applied correspondingly in the spinning frame. The last one, this is significant for fields such as oceanography and meteorology, where it makes more sense to describe atmospheric and oceanic dynamics using an Earth-fixed rotating coordinate system. For summary in this part, in order to accurately apply Newton's law to the equation of motion in rotating frame, the Coriolis and centrifugal forces must be added, or equivalently, the acceleration must be increased by the Coriolis acceleration. This enables the description of motion in relation to the Earth's rotation.
Rotating coordinate systems and non-inertial reference systems plays a crucial role in various aspects of everyday life. For instance, amusement park rides like carousels and roller coasters create centrifugal forces that push riders upward, a sensation resulting from the ride's spinning reference frame. Similarly, when driving around bends, passengers experience a push to the outside of the frame due to the centrifugal force in the car's rotating reference frame. On a larger scale, the Earth's rotation gives rise to significant phenomena such as the Coriolis effect, which affects weather patterns and ocean currents, and the Foucault pendulum, which demonstrates the Earth's rotation by maintaining a consistent plane of swing as the Earth moves beneath it. Wind turbines serve as a practical example of rotating coordinate systems in everyday applications. These turbines feature revolving blades that encounter centrifugal forces and are influenced by Coriolis forces from the surrounding airflow. Engineers must account for these forces during blade design to ensure they withstand stress without failure. Centrifugal forces exert outward pressure on the blades away from the main shaft, while Coriolis forces alter airflow around the blades, directly influencing their performance. Effective analysis and management of these forces are crucial to ensuring the blades are both durable and efficient in capturing wind energy. The nacelle houses critical components like the generator and gearbox. It rotates to face the wind, which is essential for energy capture. Engineers must account for forces on the nacelle during rotation to ensure smooth and efficient operation. These includes handling inertial forces and managing structural stresses on the tower and foundation. Next, understanding and adjusting for forces in non-inertial frames ensures smooth operation and maximizes energy extraction. Integrating fault detection and diagnosis into gain schedule controllers enhances reliability. The adaptive control method developed by Leo et al. In 2020 adjusts the control strategy in real time to accommodate changes such as ice formation or blade wear, thereby.
Hi, my name is Nurul Nafisa binti Sulaiman. I am going to explain about the problem and solution in wind turbine according to rotating coordinate system. Even though wind turbines are strong, sophisticated, and technologically advanced, they still face significant problems due to blade failure. However, a variety of solutions can effectively address this issue. All wind turbines use blades to produce electricity from the wind energy. As the wind passes through the turbine blade slides into it, slowing its speed. Longer blades improve wind turbine efficiency through aerodynamics. All wind turbines are designed to produce maximum power output at the most likely wind speeds of 15 meters per second or 33 knots, which means it would be uneconomical to design them for use at higher wind speeds. To extract more wind energy, multi-megawatt wind turbines are typically designed and built with large rotors and slender towers. These structures are vulnerable to external dynamic forces such as wind, wave, and seismic forces. These environmental forces can collapse the wind turbines. Wind turbines are designed to produce maximum power output at the most likely wind speeds. The solution to avoid this catastrophe is the physical characteristic of magnetorecological fluids. MR fluids are utilized by magnetorecological dampers. The use of MR dampers reduces bending stress at the base of 1/20 scale wind turbine tower. Wind turbine requires a low-profile bracing system to prevent interference with the blades due to their tall towers. MR dampers reduce the number of wind turbine blade failures and increase wind turbine efficiency.
In short, non-inertial reference systems help engineers manage forces like centrifugal and Coriolis forces that impact rotating parts like blades and nacelles in wind turbines. These systems allow for stronger and more efficient turbine designs by considering how these forces affect performance. Advanced control systems like individual pitch control use non-inertial frames to balance uneven loads, boosting turbine lifespan and performance. Magnetorecological dampers reduce vibrations and extend component lifespans by addressing blade failures from material fatigue and environmental stress. Overall, understanding and controlling forces in rotating systems enhance turbine durability, reliability, and efficiency, supporting the growth of renewable energy.
Given information, a large wind turbine has blade length of 40 meters. Angular acceleration of blade is 0.2 radian per second square. Initial angular velocity of blade is 5 radian per second. And wind turbine power is 1.5 megawatt. And here is the calculation.
That is all from us. Thank you.